You've watched fire 1,000 times, candles, stoves, campfires, and your brain tags it burning as if that explains anything. Let me be annoying. What do you mean, burning? Fire isn't a substance sitting on top of wood. It's a process. And the puzzle is right in front of you. Wood can sit in oxygen for years. The air is full of O2. The fuel is right there. If the end result is so natural, why doesn't the room light up by itself? So whatever fire is, it isn't just things like to combine. Something has to start it, and something has to keep it going. Hold on to that. Because the answer isn't a mystical ingredient called fire, it's a very specific kind of atomic rearrangement. And it begins with a gate you have to get through. When wood burns, atoms are trading partners. The fuel is made of big, tangled molecules. Oxygen in the air comes as O2, two atoms paired up. In the flame, carbon and hydrogen from the fuel end up bound to oxygen instead. Those new products are, in a plain sense, more stable, and that more stable shows up as released energy, mostly as heat, sometimes as light. A lot of the material leaves as invisible gases, which is why the solid seems to vanish. So fire isn't destroying matter, it's changing the bookkeeping. Same atoms, new molecules, energy paid out. Now the real question comes back sharper. If the after state is downhill, why do I need a match? Because downhill isn't enough. There's a first step that almost never happens at room temperature, and that's where the spark matters. People imagine reactions like magnets. Fuel meets oxygen and snap, they stick. Real molecules are rude. They collide, they spin, they bounce. Most collisions do nothing. Not because the reaction is impossible, but because it's picky. You need the right orientation, and you need enough energy concentrated in the right place for a brief moment. Think of a hill. On one side, you have fuel plus oxygen. On the other side, you have the burned products lower down. The system wants to be there, but you still have to get over the top. That top is the activation barrier. At room temperature, there are countless collisions, but too few have the punch to cross that barrier. So the room stays quiet. A spark doesn't add fire. It kicks a tiny region over the hill, and once a few reactions happen, they change the odds for the next ones, fast. Here's the payoff. The first successful reactions release energy into the neighborhood. That energy becomes motion, hotter molecules, stronger collisions. And temperature isn't one speed, it's a spread. Most molecules are moderate, a few are fast. When I warm the region, I don't just nudge everything upward. I create more of those high-energy collisions that can hop the barrier. So one reaction makes the next reaction more likely. More likely reactions make more heat. More heat makes even more reactions likely. That's the feedback loop. If heat leaks away faster than the chemistry can pay it back, the loop dies. If fresh oxygen and fuel keep arriving, the loop sustains itself and moves as a front. That's why a flame can be steady and why it can flare when air rushes in. So the match is only the trigger. The flame is the loop. Now let's name what the loop is producing, because heat sounds vague until you zoom in. When people say the fire spreads, they picture a thing crawling across the fuel. What really spreads is a hot reaction zone. A patch reacts and releases heat. That heat flows into nearby material and nearby air. The next patch gets warmer, and suddenly its reaction rate jumps, not smoothly but sharply, because more collisions can finally cross the barrier. So the front advances. Chemistry makes heat. Heat makes chemistry easier. Easier chemistry makes more heat. That's the personality of fire. It's self-amplifying, but only inside a narrow window. Too much heat loss and it goes out. Too little oxygen and it chokes. No fresh fuel and it starves. And that's why flames have shapes. They live where mixing and temperature and supply balance out. Now, if you want to understand fire without poetry, you have to understand what heat is physically, because heat is not a fluid, it's motion. Let's zoom in. Heat is just energy in random motion. Molecules translating, rotating, vibrating. Temperature is a way of talking about the average energy of that chaos. So when a reaction releases energy, it doesn't hand you a label that says heat. It makes faster molecules and stronger vibrations. Those smash into neighbors, sharing energy, raising the local temperature. That's why hot gases expand and rise. That's why a flame can warm things nearby. The products are moving faster, pushing outward, carrying energy away. A flame exists where energy is pumped into that molecular chaos faster than the surroundings can steal it. It's a balance between production and loss. So I can say it cleanly. Fire is a region where chemical rearrangements convert stored chemical energy into random molecular motion quickly enough to keep the rearrangements going. Now I want you to see the almost reactions that fail, and the moment the process stops being random and becomes inevitable. Let's do a thought experiment with molecules. Imagine a sealed, clear box with air and a piece of dry fuel inside. Everything is at room temperature. Nothing happens. Now give me a ridiculous superpower. I can see molecules and slow time down. I watch oxygen slam into the surface. I watch the fuel jiggle and flex. Collisions happen constantly, an absurd number of them. And yet almost all fail. Wrong angle. Not enough concentrated energy. Bonds start to strain and then relax. It's almost chemistry over and over. So the system is downhill overall, but it's stuck behind a gate. Room temperature motion rarely crosses the barrier. Now I do one small thing. I don't add fire. I add a tiny hotspot, a brief pocket of higher energy. In slow motion, the statistics change. More collisions cross the barrier. A few bonds break and reform. And the instant that happens, the next step is the key. Those first reactions don't end quietly. They pay forward into the same region. Those first reactions dump energy into their surroundings. Nearby molecules move faster. Faster motion means more barrier-crossing collisions. More collisions mean more reactions. The hotspot becomes a self-feeding zone. What you'd see is not a thing attaching itself to the fuel. You'd see a moving region where the gate stays open because the reaction keeps it open. Some energy comes out as light, excited molecules emitting photons, and often tiny hot particles glowing because they're hot. But the sustaining mechanism is the feedback between chemistry and temperature. Now notice the rule. The flame lives only where fresh oxygen can arrive, and heat production beats heat loss. Change those, and it disappears. So the title becomes literal. Fire isn't burning, it's running a feedback engine. And once you see that, extinguishing stops being mysterious. It's just a way to interrupt the engine, and there are only a few ways to do it. To kill a flame, I don't fight fire. I break the loop. There are only a few knobs. I can cool the reaction zone so collisions stop crossing the barrier often enough. I can starve it of oxygen so the chemistry can't continue, or I can remove the fuel so there's nothing left to rearrange. That's it. Water works mainly because it's a heat thief. It soaks up energy as it warms, and it soaks up a lot more when it turns to vapor. If it pulls heat away faster than the reaction can replace it, the feedback collapses. Smothering is the same logic. A blanket isn't anti-fire. It blocks oxygen delivery. No oxygen, slower reaction. Slower reaction, less heat, fewer barrier-crossing collisions, and the flame falls back behind the gate. But there's a catch that matters. Flames don't live in still diagrams. They live inside moving gases. So whether you extinguish or feed a fire depends on flow, and flow is what gives flames their shape. Look at a candle. The flame isn't burning the solid wax. The wax melts, climbs the wick, vaporizes, mixes with air, and reacts. The flame sits where mixing and heat balance work out. Now blow gently. You push the hot zone away from the fuel vapor. You replace hot gases with cooler air. You increase heat loss. If you do it right, the loop can't pay itself forward, and it dies. But fan a bigger fire and you can do the opposite. You bring in more oxygen. You improve mixing. You feed the engine and it brightens. So air is not automatically an extinguisher. Air is oxygen delivery. And because hot gases rise, a flame also builds its own little circulation. Hot products go up. Fresh oxygen gets pulled in from the sides. Fire is chemistry coupled to fluid motion. So far, this explains how flames start and sustain. Now I want to hit the deeper question. Where did the fuel come from? Not the log on the ground. It's atoms. Where did the mass of wood come from in the first place? Here's the common mistake. You look at a tree and assume most of its mass came from the soil. So you imagine the tree eating dirt and turning it into wood. But you can test that idea with simple bookkeeping. Dry the soil in a pot, weigh it, plant a seedling, and let it grow. After a long time, dry the soil again and weigh it. The plant gained a lot of mass. The soil did not lose anywhere near enough to explain it. So the bulk of the tree didn't come from dirt. That should bother you because a tree is heavy. Where did the atoms come from? Some minerals come from the soil, sure, but the main skeleton of wood is carbon-based. And the biggest accessible source of carbon is carbon dioxide in the air. The air isn't nothing. It contains CO2. A plant is a machine that takes carbon from CO2 and builds large molecules. And it also uses hydrogen that ultimately comes from water. Now you might say, fine, it can grab carbon. But building those molecules is uphill chemistry. So what supplies the push? That's where sunlight enters, and it changes the whole way you see a flame. A tree is a chemical factory powered by light. Photons come in, and some of that energy gets stored as chemical potential. In rough terms, the plant uses sunlight to drive reactions that turn CO2 and water into more complex carbon compounds, while releasing oxygen. Don't get stuck on the full recipe. The direction is the point. It's pushing chemistry uphill, taking stable molecules and assembling a fuel that can later run downhill. That's energy storage, like lifting a weight. Now fire is the reverse direction. It lets those constructed molecules slide back down toward more stable products. And the height you stored with sunlight is paid out as heat and light. So when you watch a log burn, you're watching delayed sunlight being released fast. Years of slow storage, minutes of fast payout. That's why flames can look like they have their own power. They do, but it's borrowed power. Now zoom out one step further. Fire needs oxygen, and oxygen itself is not guaranteed. The fact that you can even have a campfire is tied to biology and history. So let's connect fire to the planet's bigger loop. People treat fire as something primitive and inevitable, but fire is picky. It needs oxygen, and a planet doesn't automatically come with lots of free oxygen. So the ability to light a match is connected to life. Photosynthesis uses sunlight to push chemistry uphill and releases oxygen as part of that process. In that sense, the opposite of fire isn't water. The opposite is photosynthesis. Fire takes fuel plus oxygen and runs downhill, releasing energy. Photosynthesis takes stable molecules and, using sunlight, builds fuel uphill, storing energy. One is payout, the other is storage. So when wood burns, you're undoing what plants built. You're closing a loop in a planetary circuit. Sunlight in, chemical storage, then release. Now here's a crucial twist. Even if a reaction is downhill, it won't necessarily happen fast. Barriers matter. Paths matter. And life is a master of paths. Life doesn't jump one big barrier by brute heat. It breaks the descent into many small steps, each made easy at ordinary temperatures. That means life can burn without flames. Which brings us to a provocative question that's actually technical, not poetic. Is breathing a kind of fire? In broad strokes, yes. Breathing is oxidation. Food is fuel. Oxygen is the oxidizer. The products are more stable, and energy is released. The difference is the route. A flame releases energy in a violent shortcut, mostly as heat and light. Your body can't afford that, so it takes controlled steps. It uses molecular machinery that makes certain reactions easy without needing a high temperature. That lets energy be captured in usable chunks, so cells can do work, rather than dumped all at once as heat. Some heat still comes out, and you constantly leak it to stay alive. So I'm a slow, disciplined version of the same downhill chemistry. Now look at the full picture we've built. Fire is a feedback engine that turns stored chemical energy into random molecular motion fast enough to sustain itself. The fuel often exists because sunlight stored it via plants, and oxygen exists in abundance because life reshaped the atmosphere over a long time. So the calm room full of oxygen and fuel isn't a contradiction, it's a system sitting behind a gate. And that leads directly to the last thing I want to pin down, how we know this isn't just a story. We can measure it by light, by heat, and by the gases themselves. So why is the world full of fuel that doesn't react? Paper in air, food in air, a log in air. If the burned products are more stable, why doesn't everything quietly finish the job? Because downhill isn't the same as fast. A reaction can be favorable and still be blocked by a gate. At room temperature, most collisions are weak, misaligned, brief, so nothing happens at a noticeable rate. Fire is what it looks like when the gate is kicked open in one small place and the process keeps it open. Heat changes the odds. A few reactions happen. They release heat. That heat makes more reactions likely. Now you have a moving reaction zone. That's why a flame is local. It spreads where the loop wins. It dies where the loop loses. And once you think this way, you start wondering how people ever explained fire without measuring anything. Historically, if you don't measure, you invent a substance. For a while, people talked as if burning released a hidden ingredient from matter. They even gave that idea a name, like it was a real thing you could bottle. It feels plausible until you trap the gases and keep score. In a closed setup, the air isn't just scenery. Oxygen gets used up. New gases appear. Mass doesn't vanish. It moves into the air. Once you accept that, the mystery changes shape. Fire isn't a spirit leaving the wood. It's atoms rearranging with oxygen, paying out energy. That shift, story to bookkeeping, is one of the cleanest upgrades in science. You stop asking, what essence escaped? You ask, what changed exactly and how much? Now that viewpoint forces a connection. If fire is oxidation done fast, then breathing is oxidation done in steps. So let me go there carefully. When I breathe, I'm not adding life. I'm feeding a controlled chemical descent. Oxygen comes in. Fuel molecules from food are already there. The system runs downhill towards stable products, releasing energy just like a flame in broad outline. But my body can't take the shortcut. A flame dumps energy quickly into heat and light. That would cook me, so biology uses pathways, many small steps. Each step releases a manageable amount of energy that can be captured to do work. The leftovers become heat, and I leak it constantly. If I sprint, that leak can't keep up, and I warm up fast. So yes, I'm a kind of slow, disciplined fire. Same direction, different route. Now here's the twist. All of this assumes oxygen is plentiful, but oxygen doesn't have to be in the atmosphere at all. So where did it come from, and why does it stick around? Free oxygen is chemical tension. It wants to react. Over a long time, the reason it became abundant is tied to sunlight and life. Photosynthesis uses light to push chemistry uphill, building reduced carbon compounds and releasing oxygen as a byproduct. If enough of that carbon gets locked away over geological time, oxygen can accumulate. So the air I breathe is part of a planetary bookkeeping system, not a default setting. Now connect that back to fire. A flame is what happens when stored fuel meets accumulated oxygen and, locally, the gate opens. The loop runs as long as mixing supplies oxygen and heat loss doesn't kill it. And this isn't just a grand story. Each piece leaves fingerprints you can measure today. So I'll give you 3 modern checks, light, heat, and gases, that make the whole picture hard to argue with. Let's take them one by one. First, the light. A flame's color isn't decoration. If I send that light through a spectroscope, I usually see a warm glow from very hot particles, and on top of that, extra fingerprints, features tied to specific atoms and molecules in the flame. That tells me what's present and what conditions look like. Second, the energy. If burning is stored chemical energy paying out, I should be able to measure the payout. In calorimetry, I burn fuel under controlled conditions and track how much heat shows up in a known thermal mass. That's engineering-grade bookkeeping, not poetry. Third, the chemistry of the air. Oxygen should drop. Carbon dioxide and water vapor should rise. With basic sensors or infrared absorption, I can watch that happen in real time. Now for the last link, the carbon in the fuel itself and how we can trace where it came from. If you claim a tree is built mostly from air, you'd better be able to test it. Modern chemistry can. Carbon isn't just carbon. It comes in isotopic mixtures, and those ratios act like subtle labels. Plants pull carbon from atmospheric CO2, and that signature shows up in the wood. You can follow the atoms through the cycle, so now the title lands. Fire isn't burning as a mysterious action. It's a feedback engine that opens a reaction pathway and keeps it open. It converts stored chemical order into chaotic motion, heat, and sometimes light, fast enough to sustain itself. That's why it needs ignition. That's why it spreads as a front. That's why it dies when you cool it, starve oxygen, or remove fuel. And that's why a flame on your desk is connected to the sun over your head by nothing but honest accounting.